Okay, good afternoon, guys. So the problem solvents for today, and we will actually solve sets of problem solvents for the first one. Um, so we will finish the linear regression. And we will start the linear model for classification task. Yes. Yeah. So first, I want to show you that in last week notebook with gradient descent, there is the second part with data set from your current homework, and you can use code from here for data preparation, like one hot encoder and removing missing values. You can just copy paste and you will get the metrics ready for working with, like, for feature selection. And also I want to kind of wrap up the regression topic with scaling of the targets. So we talked about scaling of the features, but you can also scale target, and I want to show you the result. So I will open it in Colab. Okay. So I will just run the cell with gradient descent. Mhm. And upload this data set with cars. And yeah, here is this data set. So the target is the last column, the car price. And for now, I will use just one column from this data set. Oh, this is the pre-processing that you can use for homework. And you will get this table without nominal features. So I don't remember what this feature stands for, number 13. But let's fit this linear regression with features from column 13 and target from the last column. So this is how our linear model will look like. And now I want to introduce so-called logarithmic scaling of the target. So I will transform my target as log of 1 plus target. So 1p stands for 1 plus x. And I will fit the linear regression with scaled targets, and I will plot it. So yeah, you can see that after scaling, this kind of quadratic shape now, and we have large values in target here, the price. After applying log, the values are much lower because, as you remember, log function goes below function y equals x. So large values will be uh, transformed into lower values. And if I fit now the linear model with scaled target, to get back, I apply inverse transform, exponent and -1. The results will look like this. And as you can see, it fits our data better than unscaled target. So why it's performs like this? If I plot histogram of target, um, the hist of y train, you can see the some targets with high price values. If I apply logarithm, um, you'll see the distribution became more uh, similar to normal distribution. Like in previous case, it looks more like exponential distribution. In this case, it's more symmetric. So this is one of the reasons why the scaling, applying logarithms to the target helps to fit our data better. And it's called, in general, this transform is called Cox transform. And in econometrics, it's a standard transform that people apply to their data. So it can be logarithmic, and it can be a little bit different, polynomial, depending on alpha. Um, this histogram shape. Uh, so you choose this alpha or logarithm to make this distribution of target closer to normal distribution. And then linear models perform better. Okay, so that's it about regression. And now I want to use this linear model for classification task. So let's look at this picture. 1 second. nodes. So assuming we have these data points, and we have class 1 and -1, why don't we visualize these data points in three-dimensional space? So in three-dimensional space, it will look like this. The points, so x, this plane stands for the features, x1, x2, and this axis stands for the height. So the points with label 1 will lie on the plane with height 1, and the points with class label -1 will lie on the plane with height -1. And we want to predict these classes 1 and -1 with a linear model. It means that we want to fit a plane in these points, but so this, for example, the true value of y, but our model will predict this point with a value different from 1. In this case, it will be higher. And this will be y hat 1. For example, for negative class, we have 1 point here. It will be, for example, y2, but the prediction will lie on this plane somewhere here, and this will be y2 hat. So how to organize the classification? Our model, as you remember, is the linear model W transpose times X tilde, extended by 1. But we want somehow to classify, like for large values of y, we want to assign class 1, and for small values of this linear function, we want to assign class -1. So what do you think? How can we actually build this algorithm, build the decision rule that will classify our points based on the position on this plane? So this height is y, this is y, this is x1, for example, this is x2. These are features. This is the prediction. Yes, Ross.
Maybe we say something like y greater or less than 0 or something.
Yes, it's a good idea to set some threshold. So, for example, in this case, we can use 0, but it will be easier to me to assume that these labels have value 1 and these labels have the value 0, then maybe I should choose threshold as 0.5. So, for example, 0.5. And if I draw the plane that goes through this 0.5, the intersection of two planes will result in a line. And all the points that lie on the predictions that lie on my plane above this line, I should classify as 1, and all the points below I can classify as 0. So in other words, I can use the Iverson brackets notation. If my prediction is greater than threshold 0.5, I will return 1. So if the prediction is higher than 0.5, it will be true, and the Iverson brackets results in 1. If it's smaller, it will result in 0. Does it make sense? So this is how we can actually use linear model, which predicts continuous number between negative infinity to infinity, to the classification task, where target takes only two values, 0 or 1. Does it make sense? Okay, so if you look at this problem from above, let's take a look from different angle. Then you will see this two-dimensional image. And if we draw this threshold separation line, and again, if you look from above, then you will see kind of two-dimensional classification problem where we try to fit a line that will separate our points such that we have the smallest number of errors in our classification. So this is the another point of view, and let's look at the so this is the two-dimensional projection of our image. Okay, so let's talk about metrics for classification. So this matrix, it's called confusion matrix. So this will be our first problem. Yeah. So we have our true values and we have our predictions. So, well, in this case, I have 1 and -1. And so the class values can be, for example, 1 and -1. But predictions also can take values 1 and -1. So if our prediction predicts our point as class 1, and this point was labeled as class 1, we call this true positive. If our point had a label -1 and our model predicts -1, we call this true negative. If our point, so if we go back to illustration, if our point, for example, if this red line we draw a little bit higher, then some points with label 1 will be classified as 0. So in other words, if our model for a point with label 1 returns a different label, we call this false negative. It was positive, but the prediction was negative. False negative. And finally, if our true target was negative, but our model predicted this as positive, we call this false positive. False positive. So let's calculate these metrics in two cases. So in first case, our threshold is 700. It means that all the predictions um, for the, and also I sorted our data points by the linear function, by this y-axis. So every point with linear function greater than 700 will be classified by our model as class 1, and points with this linear function smaller than threshold will be classified as -1. But here we have true labels. So based on this, we should populate our metrics. So for example, how many true positives? You look at the upper part of your table, because in upper part, the model predicts everything as positive. So here you'll see only two true positives. How many true negatives? You will look at the second part of your table and count how many true negatives. Should be 1, 2, 3, 4. Then to calculate, for example, false positive, you look at the first part of your table, because these points were predicted as positive, but one point actually had label -1. So it means that we have one false positive. And then you should calculate how many false negatives. It means that the prediction was positive, but the true label was positive, but prediction was negative. And for the second problem, you have a little bit different threshold. So please calculate two matrices for one threshold and for another threshold. And then we will talk about precision and recall metrics, because we will calculate them based on computer metrics. And as you remember, you can communicate during problem solving with other students or ask questions. Okay, did you get the first matrix 2215 and the second, I don't remember, something 2410, something like that? Let's see, the second, how many true positives? 1, 2, 3, 4. Yeah, so it will be 4. Then false negatives 0, so it will be 4, 0. False positive 1, 2, 3. Yeah. So it's 2, 4. Okay. So is it for 0, 4, 2? Okay. Okay, so now let's talk about uh, the main metrics, which are precision, recall, and F1 score. So um, precision and recall. So the recall is easier. So I will start with recall. It's the number of true positives over the total number of positives. Or what does it mean, the total number of positives? It means that it's true positive plus the model that model predicted incorrectly as negative plus false negative. And if you look at our table, um, true positive plus false negative will be this row. So this will be the total number of positives. So in other words, we divide the correct guesses of the positive class by the total number of points in the with label 1. For precision, we divide the true positives by the total number of the points that our model predicted as positive. So it means we divide by true positive plus false positive. And if you look at the table, it will be this column. So we divide the total number of correct guesses by the total number of the data that our model predicted as class 1. Now let's look at the difference. So let's say we have uh, some data um, and okay, I will just open it from my lecture notes. It will be easier. So let's say we have two different cases. The first case, our model predicts just a small amount of data as class 1, but most of these predictions are correct. They also have true label 1. Let's think about, for example, we have formula for recall here. So recall is the total number of true positives over total number of positives. What do you think recall will be close to 1 or close to 0 for the first situation? We divide the area of the red ellipse by the area of the yellow ellipse. Small. It will be small. Let's think about second situation when we have this model prediction and it actually predicts more points than it should be by positive class. What will be the recall in this case? What will be, which ellipse will correspond to true positives? Red or yellow?
One.
It will be 1 because true positives will be this yellow ellipse, but also real positives will be. So, okay, it means that if our model kind of in the worst case predicts everything by class 1, it will have the perfect recall. That's why we use two metrics. The other metric is precision. And precision, I don't have the formula here, but it's the number of positives divided by the number of the positive predictions of our model. So in the first case, what will be the precision? So this red ellipse corresponds to numerator, true positives, but the same ellipse corresponds uh, to total number of the points that our model predicted as correct class. So in this case, precision will be 1. You remember, recall here was low, precision will be high. In this case, recall was 1, but precision, we should divide the yellow area by the total prediction as correct class by red area. So precision will be lower in this case. Does it make sense? So now let's think about situations when we want to use precision and when we want to use recall. So for example, if you develop a medical test, what do you think? Which situation is better for medical test if I want to, for example, detect a sick person? When we predict just a small group correctly, or when we predict also normal people as sick, but we cover also all sick people. So what do you think is better for in this case, in the medical test?
Precision.
What about the images? Precision, high precision corresponds to this one, or for this one? I believe for this. Precision was 1 here. You're correct. So this image actually is better, because in this case you will your test will say to a normal person that they're sick, but then they can take another test. But at least it will cover real sick people. So you were right. Precision, which is the number of true positive. Oh, no. Sorry. Wait a second. Precision was 1 here. So recall is better. Recall is better. Because recall will be 1 here. It's the true positives, the yellow circle over the yellow circle. So in this case, we want to maximize recall. Now let's think about another task. A bank decides to give the credit or not. So what do you think? Does bank wants to get all the credits back, or maybe bank wants to give as much as like more credits to get more interest, but maybe some people won't return this credit. What do you think? Bank want to maximize. So if bank maximizes this metric recall, then it may reject some people with money, even though, I mean, the model won't like maybe credit score or something else, and they will reject the credit, but maybe that person actually could pay. In this second situation, if we maximize precision, um, um, how to interpret that? So my idea was that uh, bank can allow some losses that some people won't return the money, but uh, getting more clients, the bank will get more interest. Um, and in this case, we should maximize precision, if I remember correctly. But how to see this from this paper or from this plot? Um, so so you remember precision is the fraction between true positive and points that our model predicted as positive. But our model could make errors. So in denominator, we had true positive plus false positive. So if we maximize precision, um, we want to well, but still, we actually will our model will choose like people that actually will return the credit, but still it allows some errors. So my point is that um, we don't want okay, I think I should reformulate this task as to reject the credit. So in this case, our model will let's see, reject more people than in this case. Okay, I hope you get the idea that sometimes we want to maximize uh, recall to cover all uh, points from positive class. Sometimes we want to maximize precision. For example, if we want to hit a missile, then we don't want to spend a lot of guns. We can just fire when we are sure that this missile actually will anti-missile will hit the aim, the goal. So in this case, we maximize precision. Does make sense? So we don't fire to every goal, but if we fire, then we will actually get this object. Okay, target. So yeah, let's calculate precision and recall for our two problems. Did you calculate those? No, I mean, it's still on the first page. Uh, and you will see that when our decision boundary is low, it means that we predict more points as positives. So you will get higher higher recall. If your decision boundary is higher, then you will get better precision. Oh, did you copy? Yeah, so yeah, it's one, and this is the precision is higher here. First, you can look at the next page and think about combining these two metrics in one. So the next page is about combining these two metrics in one metric, so that we can maximize one metric, but both will be maximized. And it's called F-score. So there are two options. One is just linear combination. Another is called geometric mean. So, so the first formula is just the average of precision and recall. The second is the average, but it's called of inverse geometric mean P, 1 over precision plus 1 over recall. If you find the common denominator, you will get exactly this formula. And you can think about this as a function of two variables, precision and recall. And then when you visualize this function of two variables, in the first case, it will be just a plane. And in the second case, this function will be a nonlinear function. And here, the visualization of this surface. And the question is, which function will represent better? So I will phrase it as follows. When the high value of function will result in high value of both and precision and recall. So if you look at the first image, like this value about 0.9, then you can see that you can get 0.9 with 0 precision and 0.9 recall, or with 0 recall and 0.9 precision. So it means that the value 0.9 for this function you can get with either 0 precision or with 0 recall. If you look at the second plot, and these lines, they are the lines of the constant value of your function. For example, if here is 0.9, then it will correspond to high value and precision, and precision will be in this range, and also for high value of recall. So which function is will maximize both and precision and recall? The second one. So that's why the first idea is not working if we just want to take the average and maximize that. So that's why people are using so-called F score. In this case, it's F1 score. When we maximize this function, then we maximize both precision and recall. Okay. And the more general formula here, F beta score. If beta is 1, then you will get 2. Okay, so for the last problem, I just asked you to calculate this F1 score for problems from previous page. You calculated precision and recall in previous page for 2 problems. Now I asked you to calculate F1 score, and I hope you will get higher F1 score for the first threshold. Then of the second. Correctly. Yes, but yeah, you can just ask maybe other students have the same question. Yeah. No, just calculate two F was four for first two problems, like for the first and for the second. No, the first one, I asked just to write the reasoning, which function we should choose. I try to explain that. Hey, and after we're done, we're going to the second set of problems for today. Maybe I can pass to the second. Or you could also write which one you should suggest. So in the third problem, you should write which method would want to use the combination of two. If you have any questions, yeah. Maybe other students have the same questions. Yeah, I have one close. Sorry, did you get five F1 score for the first one? Or I think it's I don't know. Guys, is the F1 score higher for the second one or okay, then you're right. I didn't remember for it. Okay. Yeah. It's from the third problem that which is that. No, okay, can we go? Can we move to the second part? So now we will look at our data from above. So now we will change our point of view from 3D into 2D. So now we won't think about the value of this. Well, actually we will, but we won't interpret this value um, as the altitude. So we will now let's talk about geometry of this linear classifier. And the first problem is just to remind you that the coefficients of linear function, this W coefficients of linear function, they are actually they represent the normal vector to this line. So if we have the line that goes through the origin, so I don't have a bias, then if I take a point on this line, for let's say here is the origin, the point on this line will have coordinates x1, x2, x1, x2, and I denote this as a vector from origin with coordinates 0, 0 to x1, x2. So then I have these coefficients, and I want to multiply this vector W, times x. So it will be the product of vector with coefficients W1, W2 times my vector that goes from origin to a point on a line, x1, x2. So if you take the dot product, you will get this W1 x1 plus W2 x2. And from the equation of the line, it equals 0. And when the dot product equals to 0, dot product is the absolute value of the first vector times the second times cosine, when cosine is 0, when the angle is 90 degrees. It means that W and X are perpendicular, and we've solved problem 1. So vector W will be perpendicular to our line. So it's just a reminder from maybe school geometry. So next problem is when we have now we have our line. Again, this line, for simplicity, goes through the origin. The line has equation W1 x1 plus W2 x2 equals 0. So we don't have a bias term. It's just easier to understand. And then we have a point somewhere, point x with, well, I'm using x1, x2, let's say x1 prime and x2 prime. So we have this vector x prime. And the question is, what is the distance d, from this point to our decision boundary? So this is what I'm interested in, this distance. How to calculate the distance from any point on this plane to our separator. What we know from previous problem, we know the components of the vector along this line, the perpendicular, which is W. So what we know the vector perpendicular to our line, which is W. So how using x prime and W to find the distance? We should take the projection of vector x on this vector W. Does make sense? And projection has this formula. So projection is the length of our vector times cosine. And length of our vector times cosine is just the dot product divided by the length of the first vector. So if you want to get the length of vector times cosine, you can take the dot product over the length of the first vector. So let's use this formula. So it will be, so distance will be a projection of our vector x prime on vector W. Or it will be a dot product, and the dot product is just W transpose times x prime over the length of vector W. And if you look at the formula above, I just need to use prime everywhere for x. You will get this formula. So numerator is the dot product between vector W and x prime, and denominator is the length of the vector W. So this is how you can calculate the distance from any point to the decision boundary. So you remember, in 3D, we calculated only numerator. But if you normalize this numerator, you will get, in 2D, you will get the distance to the decision boundary. Okay, if you don't have questions, let's move on the... So does anyone have questions about distance? Okay. The last problem will be to find the distance from a point to a line that doesn't go through the origin. But before we move to that general line position, let's introduce a new notion, which is called margin. So margin, by definition, is this value, is just the product of our dot product, or our model prediction, and the target. And I want you to prove that the margin will be positive for correctly classified points and negative for incorrectly classified points. And then it will actually give us an algorithm how to find this decision boundary. We will try to maximize margin, because positive margin will classify points correctly. So let's consider 4 cases. So first case, when our target is positive, y is positive, and our prediction, because this Wx is the same as prediction, is also positive. You remember, it shouldn't be exactly 1. It can be an arbitrary number, but so which sign does this product have? Positive, yeah. So if we have so if our, so again, a little bit about visualization. So on this line, our prediction is 0. Wx is 0. Like above, the Wx will be greater than 0, and below, Wx will be negative. So if our point has positive target, and also the distance is positive, the product will be positive. This is the first case. So margin will be positive. Now, if our target is positive, but the prediction is negative, so it means that our point has a positive class label, but it lies like below our separator. So our model predicts this as negative class. So the dot product will be negative for this point. And when we take the product with target, the first term will be positive, the second will be negative. The third case, when our class label was negative, and the prediction was positive. So if our, so it corresponds to this point, blue. The true label is negative, but the distance, the Wx equals to some positive number, and the product will be negative. And by the way, these are incorrect classifications. And this was correct classification. So the last case, when our target is negative, and the dot product is negative, sorry, I said negative one. But the product will be positive. And again, if our target is negative and the dot product is negative, it means that our point was classified correctly. That makes sense? So we proved that if we look at only at this value, the true value, true label times the model output, then when it's positive, our point is classified correctly. When it's negative, our point was classified incorrectly. And then we will talk about algorithm that maximizes this value and finds the best W based on that. Okay, so the last problem is just generalization of the second one. To find the distance in case when this line doesn't go through the origin. So the same problem to find the distance from this point x prime to this separator. But now this separator has a bias term. So it's now W0 plus W1 x1 and plus W2 x2 equals 0. So our standard linear function. So to find this distance, we can kind of reduce this problem to the previous one. We can draw this parallel line, and we know the expression for this distance from problem 2. So this distance is equal to W. So this distance is this part without W0. W1 x1 prime plus W2 x2 prime over this length of W without W0. So the only thing remains is to prove to figure out this distance. So let's think about how we can use this bias term to figure out this distance. So what are the coordinates of intersection of intercept? So you have the equation. What should I take 0, x1? So this will be x1 or x2 to find this intercept. X1 should be 0 at this point. So x1 should be 0. So just substitute 0 instead of x1. So if x1 is 0, you will find x2, and it will be your intercept. So it will be W0 plus W2x2 equals 0. So x2 will be so this point will have coordinates x1 0 and x2 negative W0 over W2. Okay, so we have found this vector. To find this distance, we should take the projection of this vector on W, on the perpendicular vector. And we're done. So we find the projection. So this question mark is equal to the projection of my vector. Let's denote this, for example, A. On the W, because W is perpendicular to our line. So we take the dot product, and that dot product between my vector, this vector and vector W will be 0 times W1, but then minus, because negative sign here, or plus negative W0 over 2 times W2. So this is the dot product. And then we should divide by the length of vector W. So you can see that we have only W0 remain. And this W0 over square root we add in our final formula. Okay, so that's it for today. I just wanted to introduce how we can, which metrics we are using for classification, and what is the geometry of linear classifier. Uh, yeah. Yeah, so leave your papers on the desk. And next time we will talk about logistic regression.